Well, thanks for having me. I'm delighted to be here. I'm also an alumnus of the other MIT of the West down the road. I now run robotics research at Google. Our goal in robotics research has been to try and figure out what this convergence of robotics and machine learning can mean and can look like. I've seen on the agenda today that many startups that are presenting today are somewhat in that space. So I'm hoping that I can set the stage for them or give them a chance to tell you how I'm completely wrong and they're doing things much better. The background is that essentially perception at large and computer vision in particular have been really revolutionized in the last few years. And everybody has seen this. I won't belabor the point. This has been very apparent in a lot of the online world. And the really key aspect of this has been that we have now really been able to bring semantics into the picture of perception. And that's very new. Like the traditional computer vision stack was a lot about geometry, like SLAM, and things like very precise registration of objects and of spaces. And we were able to understand the geometric world around us. We didn't have access to semantics for a long time, not for a large class of objects. So this is an example of very recent work that we've done in my team, where we have semantic segmentation of all the objects individualized in images. We're able to get very high levels of recall and very precise segmentation of everything. This is just an example of this. One thing that is fascinating to me is that bringing semantics into the picture is actually also helping us understand the geometry of the world better. So if you see the picture on the left here, you don't really need to have a stereo vision or a depth camera or a LiDAR to understand the geometric structure of that image, right? You know there is a house, it's mostly a cuboid of sorts, there's a flat roof, there's a ground plane, a few shrubs, cars. The geometry of this entire thing is very much understandable based on what is in the scene. And so with the modern tooling around deep learning, we're able to take images like this from videos and just turn them into depth images that really represent the 3D structure of the images without any of the physical devices that are traditionally used for depth sensing, for instance. And all of that can be learned completely unsupervised. We can just use videos and use the relationship between things over time to understand those things. This is very powerful. This really changes the game in terms of the way we approach those kind of structural problems in computer vision. Now, that means we kind of get access to the world in all its glorious complexity, and we can start to try and understand both semantics and geometry of the world. The caveat is we've lost something in the process. And if you come from the perspective of industrial automation and industrial perception, you are very accustomed to very precise state estimation and very precise vision. Right? In the world where you know all the objects in the scenes, you have CAD models of them, maybe they're isolated, they're well registered, you control the lighting and everything, you could get very precise registration of them, positioning, and understand at the millimeter level where things were. Arguably, the modern deep learning stack hasn't measured up to that level because we're trying to generalize across things that you haven't seen before or a much wider net of objects. I want to argue that to some extent it's good riddance, in the sense that precision gives you the illusion of being very, very accurate, but it also means that you can be very precisely doing the wrong thing if your state estimation is wrong. This is an example of a robot really trusting its perception, thinking that a wheel is exactly in the right place, and based on that assumption, doing all the wrong things. Right? If you rely on that level of precision in the real world, you're at risk of not really succeeding. If you look at human perception and what people are doing, we don't operate like this. I don't have a millimeter level sense of where this door is, but I still can interact with it and navigate with it. And it's really because I'm interacting with the world, and I can understand how things relate to each other. I don't really need a super precise perception stack to be able to interact with everything because I live in the world. And so the cure to that problem is really to try increasingly to find ways to close this perception action loop. Right? And this is not new. In robotics, a lot of people have been doing this for a long time, things like adaptive control and things like this. The real novelty here is that we can now do this with machine learning. And that changes things materially. The idea now is that we can turn all of robotics into a large-scale machine learning problem, in the sense that you have now robots that can transfer their sensing to machine learning systems. So machine learning systems can understand the geometry, the semantics of the world, churn on that, and send back actions, policies, actuation, goals for the system. And once you have this loop, and you can tighten this loop very well, you have this feedback of action and perception that can happen, and this impedance mismatch between the perception and action goes away. I'll give you an example of from a few years ago that we did. This is an experiment where we put together a few robots in a lab. We connected them to a machine learning system in the cloud. The robots were not instructed to do anything in particular. They didn't have a perception stack that told them anything about the world. All we told them was that whenever they would have grasped an object and picked it up, they would get a reward. They would get +1. And if they missed the object, they would get -1. We did not tell them what an object was. We didn't tell them that our goal was really for them to grasp objects in general. All we gave them is this very weak reward. And they were all connected together. They're different robots. Their cameras are not calibrated with each other. It's a real-world-ish setup in that sense. Using deep reinforcement learning, what we were able to do after collecting data for about a month, we were able to get a system that could grasp objects. This is the one on the right, very, very precisely, almost 100% performance. What's interesting about this is that, again, the cameras are not calibrated, so we don't really need a very precise registration of everything. It's mostly looking at the gripper of the robots and in relationship to the objects, and is able to reason about this. That's this perception actuation loop. The other interesting thing is that none of those objects in the bins have ever been seen in training, so it's entirely a generalization problem. The robot had never seen the little dinosaur in there or anything like this, but understood that the geometry was enough to make it work. A lot of very interesting things developed naturally from the learning. So the robot learned to manipulate the objects pre-grasping to simulate them and make it easier for them to be picked up. The robot was able to learn about self-correcting when the things were slipping out of its grasp. We did not program that. That was entirely an emergent property based on the self-supervision. If you try to perturb the system, you can also recover very naturally. So this entire loop is learned using deep reinforcement learning. This is actually a very efficient way of incorporating this feedback loop into the process. It's a very exciting field of research right now. There's a lot of developments in deep reinforcement learning. It's still very researchy. It's still very difficult to wrangle, but there's a lot of very fast progress being made in this space. Another fun experiment that we ran is looking at very optically challenging objects. This is a really hard problem because a lot of the systems that use depth cameras, the depth sensing basically sees through the translucent material and can't really reason about them. Since we're just using cameras and we don't really need any of this heavy machinery, we're able to do pretty well in this kind of task. So it's very relevant for industrial applications. Another really interesting aspect of this is that because the learning is very agnostic and doesn't really know what the objects are, it's able to learn whatever is relevant for the system. So in this case here, we're teaching the robot to toss the objects into the right bin. And for that, you need to understand the physics, the dynamics of the objects, and correlate that with their shape. You have to understand that a banana has a certain weight, and you need to be able to throw the banana with a certain speed and a certain angular momentum so that you can go into the bins. And that was learned entirely by the system without encoding any of that information into the robot. So this is a very interesting way of looking at this system setup. It's very different from what a lot of robotics deployments looks like today. One of the interesting aspects of this is that now that we have this system that actually closes loop with a cloud-based system and machine learning and all this, we can actually bring back humans into the loop. And so, you get the sensing input, you can show it to a human, and then have the person actually do the right thing based on the task. So here's an example where we have a singulation task where we're trying to take those deodorants and put them on a conveyor belt. It's a very industrial application. We have that connected to somebody who's wearing a VR headset remotely, and the person gets to pick where the robot should be picking the objects. That gets us an operator, a naive operator, gets that to about 84% performance. We have a machine learning system that learns in the background and adapts itself and can take over from the human at any time. And when it takes over, we get about 92% pick success. We do that a little bit more, and with about almost 1 million examples and more variety of tasks and variety of objects, we're able to get to very, very high levels of performance, 98%. And that's across a variety of objects, variety of lighting condition, variety of setup, without a line of programming. So that's a very, very exciting way that things are sort of developing. We've been playing with those classes of algorithms and that setup in a wide variety of contexts. We've learned things like quadruped locomotion, either based on imitating the locomotion of actual dogs, or just from scratch. We can have a robot basically learn, teach itself how to stand just based on the reward that you get a reward when the robot has moved to a given location. We've worked also on dexterous manipulation, the same kind of setup using model-based approaches. We've applied it to navigation as well, and that enables us to bring into the navigation problem a lot more signals that are more relevant to the task, including the presence of humans, the presence of puppies. Since it's all about not connecting with the puppies, we do a lot of training in simulation. This way we don't hurt anyone. And it's a very effective way of learning very reactive policies that enable us to do a lot of different behaviors that are emergent and topical to the task. So what's really interesting from an industrial standpoint is that this is a very new model for robotics, right? People are used to taking a robot and you deploy it into a factory environment and push a button and then it goes. And then you have to change something, you bring in an integrator, the integrator changes the programming and the cycle starts anew. Those cycles times are really long, they're very slow. The way that we can obtain that level of flexibility is not something where these very heavily engineered systems can really scale to scenarios where the tasks are constantly changing and evolving. Right? So this model really changes the way you think about things. You have to think about data first, you have to think about data storage, you have to think about data connectivity, how do you bring the data fast off of your robots, how do you bring policies onto your robots quickly, how do you design the task so that generalization kicks in and you can benefit from that, how do you adapt things continuously, Having humans in the loop is actually a very efficient way of defining tasks and tasking. Humans are really good at understanding the high-level things. Machine learning is not very high-level today. And a lot of the things that we're able to do that are at the level of low-level perception work fantastically as soon as you're trying to get into very complex semantics. That's where things are a lot more brittle and a lot harder to get to work. So I'm very excited about this space. I think this is something that will really change the way people approach robotics at large. And we have a lot more research to do in this space. How do you make it faster, more efficient, more adaptive? But that's the kind of research that we're excited about. Thank you very much. I'm happy to answer questions.
Very interesting. How about a hybrid approach of generalization and perception together as
Yeah. No, you can definitely, and you benefit a lot from the classical perception stack in the cases where there is already something good and you don't necessarily care about generalizing to an instance, for example. The nice thing about modern perception is that it's something that is, when you're using machine learning and deep learning and things like this, it's a black box, but it's an adaptive black box. Meaning, as long as you have an error signal to send back to it, it will adapt to whatever task you have. And that's a very powerful paradigm because it doesn't care about how and why where the signal comes from. So as long as you can design your perception stack entirely independently, but then you can adapt it. And that really is what brings you often over the hump in terms of performance. Yeah, absolutely.
Thank you so much, Mason. That's